time. Now I'm going to define what vector space is. Okay, so the definition I must give you. So you note down the definition. A vector space or linear space, a vector space or linear space over a field F consists of a set on which two operations called addition and scalar multiplication are defined so that for each pair of elements x and y, or rather I must say xy, for each pair of elements xy in the vector space V, there is a unique element x plus y in V, and for each element small a in capital F, and each element small x in capital V, there is a unique element ax in V such that the following conditions are satisfied. I'm going to highlight a few parts of this particular paragraph. Say, for example, you also try to highlight these paragraphs, these particular points. For example, I'm highlighting this one, addition. I'm highlighting this point, scalar multiplication. And whenever I'm saying that for each pair of elements x, y in V, there is a unique element, I'm highlighting this point, this unique element x plus y in V. For each element a in F, I'm highlighting it. For each element x in V, I'm highlighting there is a unique element ax in V. These are highlighted points that you have to keep in mind. And also one important fact is the following: vector space is always defined over a field capital F. I will explain everything, but let me give you the definition first of all, then I'm going to explain each and every point. What does this particular point mean? And the properties, there are in total 8 properties that needs to be satisfied. So let us name these properties as VS1, VS2, VS3 and VS4. I'm writing these properties here, and the other properties are VS5, which is the 5th property, VS6, the 6th property, VS7, 7th property, and VS8, the eighth property. One of the students was asking me how vector space is defined. Now I'm going to define the vector space. This is the paragraph that you have to keep in mind first of all, and each element of the vector space or pairwise, they must satisfy all of these properties if the set needs to be a vector space. So what is the first property that I'm going to talk about? Carefully listen to me. First of all, for just a minute, for all x comma y in V, x plus y is equal to y plus x. This is called the commutativity property. Just look at the notation that I am using. Highlight this notation. I'm going to explain what is happening over here. So x plus y is equal to y plus x. Okay, so for all x, y in V, commutativity must be satisfied. The next property is for all x, y, z in V, for all x, y, z in V, x plus y plus z, this must be equal to x plus y plus z. Okay, just look at the notation that I am using. I'm just highlighting the important points. You have to be very careful about this. There exists an element, in V denoted by 0 bar such that x plus 0 bar is equal to x for all x in V. Just look at the notation I am using. Fourth property is for each element x in V, there exists an element y in V such that x plus y is equal to 0 bar. I am highlighting this notation here also. Now let's come back to VS5. For each element x in V, we have an element which I am denoting by this. This is not one, this is not a numerical one, this is a notation, remember. So I am bolding, I am trying to make it bold. So this 1 into x, okay, I should write over here 1 into x, I am putting a dot like this, 1 into x, which is equal to x. Just look at the notation I am using. And the sixth property is for each pair of elements A, B belonging to F, highlighting this part, and for each x in V, we have A dot B dot X, A dot B dot X. One more thing here, when I wrote X, Y in V, there is a unique element X plus Y in V. You make it this plus. And when I am writing for each element A in F and for each element X in V, you make this AX to be A dot X. Just make these corrections. Okay, and we have got this property. So this is V6, VS6. The next property that I'm going to consider is VS7. So it is VS7 goes like this. For each element, A in F, and for each pair of elements X, Y in V, we have this property that A dot X plus Y is equal to A dot X plus, A dot X plus A dot Y. I'm highlighting this particular notations that I'm using over here. Just carefully observe. I'm highlighting each of these notations. And the last property, I somehow have to manage to write it over here. VS8, the last property is for each pair dot X is equal to A X B dot X. These are this in this particular, as I told you, that vector space is a kind of algebraic structure defined on another algebraic structure. So by this I actually mean that two different types of elements are present when we consider the vector space. Okay, what sort of elements are there? One element which one type of element which is a member of the set capital V, and another element which is the member of the set capital F. The member of the V, the member of the vector space, the members will be called vectors. The members will be called vectors, and the member of the set F will be called scalars. Scalars. These are the members. These are the members of the set. So two different types of members are present. One is member of the set capital V, and another is a member of the set. So what I'm saying is that when I talk about the field structure, the operations that I considered was plus and dot. But when I talk about vector space, the operations that I have considered is denoted by plus and dot. Okay, so there are two types of operations that are playing the role. These operations are defined on the field of scalars. These operations are defined on the field of vectors. And when I wrote the properties, I highlighted these points. It's because when I consider the element X, Y in V, that means I'm considering two vectors from the vector space, from the set capital V, and they must be added together with the operation of this kind. So this vector plus has been used to denote that actually two vectors are getting added. Here also, when I talk about the associativity property, this property is called the associativity property. Each element present inside the property are actually vectors. So when I actually add them, I'm using the vector addition symbol in each and every case. For the property VS3, this element, I missed this one. So there exists an element oh no, there exists an element in V denoted by 0 such that when I considered this x element x in V, this element is the element of the set capital V, and the 0 bar is supposed to be the element of the 0 bar is supposed to be the element of the V itself, so that the two vectors when added together gives you the same vector. So here x is a vector, 0 bar is also a vector. It is not the number 0. So this operation, this vector addition operation has been used, and if such a 0 bar exists, we call this 0 bar as the additive identity. The 0 bar is actually called the additive identity of the set. Here when I talked about VS4, I considered the vector x, and for each vector I need to find out a vector y, so that when the two vectors are added by vector addition, we get the additive identity in return. So here x is a vector, y is a vector, they are getting added, so I use the vector addition symbol, and y is called the additive inverse of x. Additive inverse of x. When I come to VS5, I need to find a vector 1, a kind of vector 1. It is a vector 1, it is not the number 1, which when multiplied the vector x gives you in return the element x. So I use the symbol vector scalar multiplication. This is not the vector multiplication, this is called the scalar multiplication, as has been defined over here. So I used actually this dot. Let's come to the property VS6. Now in VS6, you carefully observe, in VS6, I actually kind of used an operation which is defined as the following. So A into B when multiplied by x is same as if you multiply B with x and then you multiply that quantity by A. Now here two types of multiplication operation have been defined. Okay, first of all, when we are multiplying A and B, I actually mean the scalar multiplication of the elements A and B of the field. So I use the dot which is given over here. But when this scalar, the multiplication of two scalar is also a scalar. So when we get the scalar A dot B, and when it is getting multiplied by the vector, this is the scalar multiplication A dot x type of thing. So I used outside the bracket, I used this vector, this particular multiplication operation, dot inside a circle. Now just look at the right hand side. In right hand side, no such scalar multiplication is there. If I talk about this is a scalar, this is a vector. So scalar multiplication dot has been used. Their outcome is also a vector, because when a vector is getting multiplied by a scalar, that means suppose you have a vector x, you are multiplying it by 2. That means the vector is getting elongated. Okay, if you multiply it by -2, it is getting contracted. So this outcome is also a vector. And since it is a vector, we want to multiply this vector by a scalar quantity. So therefore, I have used this dot under the circle, inside the circle sign. So this is the right hand side is entire right hand side is a scalar multiplication. But on the left hand side, inside the bracket, we have the multiplication of two scalars. Scalar multiplication and multiplication of two scalars are two different things. Scalar multiplication means we are multiplying a vector by a scalar quantity. And when we say that multiplication of scalars means two scalar quantities are taken and they are getting multiplied. So you have to understand what actually is meant by these terms. VS7, both left hand side and right hand side, all of these quantities are vectors. Inside it, we have x plus y. So I have used the vector addition. And here we have the scalar multiplication of the vector by a scalar quantity. So this dot has been used. Similarly, on the right hand side also, we have a dot x and a dot y. Both of them are scalar multiplication of vector by a scalar. And since the result is a vector, we are adding two vectors. So we have used this symbol. And lastly, here we have written a plus b dot x, a dot x plus b dot x. This is b dot x. So each of them are actually But here in this particular case, the inside the bracket you see two scalars have been added, and therefore this plus symbol has been used over here. Okay, so my what I mean to say is that when we operate the we do some kind of operation on the in the vector space, we have to understand by what we are actually doing, whether we are actually multiplying the vectors and adding the vectors, or we are actually adding the scalars and multiplying the vector by the scalar. These things are actually different. So I have used four different notations to make you understand this. And if it is so, if all these 8 properties are satisfied, we say that this structure V defined over the field capital F with the scalar vector addition plus and scalar multiplication of the vector, which we denote by this dot, this structure is a vector space structure. This structure is a vector space structure. Now this is the way by which a vector space structure is actually defined, and you are actually not much familiar with this kind of things that I am actually using over here, but you will gradually understand, and you will come to terms with this. Okay, so we have to work on some problems, then only you can understand what is happening over here. Now let's talk about the set of let's talk about the set of matrices that we denote by m cross n. And now previously I only wrote m cross n to denote the set of all matrices of order m cross n, set of all matrices of order m cross n. Okay, so it is an infinite set. But since now you have learned the notation of a vector space defined over a field capital F, now I am denoting this particular set by m cross n f. So I am denoting this particular set by m cross n f. Now, what do we mean by this? You have to understand the meaning first of all. Suppose you have asked me to give you to write a 2 by 2 matrix for you. Suppose I am giving you a 2 by 2 matrix like this. Suppose I am considering the matrix 0, 1 and 1, 0. This is a 2 by 2 matrix. You all know this. And suppose I am actually giving you another matrix, which is also a 2 by 2 matrix, 0, minus I, 0. Okay. Now these two matrices, these are both of them are matrices. This is a 2 by 2 matrix, and this is a 2 by 2 matrix. But structurally they are different. Why? Because this matrix is actually belonging to a different vector space than this matrix. What? Why is it so? Because just look at the elements here, 0, 1, 1, 0. All these elements, you can consider these elements to be the real numbers, because 0 and 1 are the real numbers. So we can say that this particular matrix, let us denote this matrix by capital A. This matrix belonging to the set M2 cross 2, which is defined over the field of real numbers. When I am constructing the matrix, I am choosing the matrix elements inside from the set of real numbers. If the set of real number, if this is not there, I shall not be able to construct the matrix because the elements are then missing. So this is a particular matrix which is defined on the structure this, whereas the second one is actually defined on another set of matrices, which is of order 2 by 2 definitely, but it is defined on the set of complex numbers, because these elements are complex numbers, and here 0, all these zeros are also considered to be the complex numbers, because 0 can be represented as 0 plus I into 0. So here these two matrices, therefore let us denote this matrix by B. So these two matrices are structurally different. So this particular matrix is defined on this set, which is defined over the field of real numbers, and this is defined defined in the set this, which is defined over the set of field of complex numbers. So that what we actually mean but when we write M cross n F. That means I am constructing the matrix, but the question is from which particular field I am choosing my matrix elements. This is the first thing that you have to understand. The second important thing is that if I consider a matrix M cross n F, okay, and this matrix that I'm considering, if I use the operation plus and I consider this operation as matrix addition, and if I denote the operation dot by scalar multiplication of a matrix by a scalar quantity, scalar multiplication of the matrix by a scalar quantity, if I denote the operations like this, the question is this structure a vector space or not? That we have to consider. Here the assumption that I have made is this, that in general, since I'm giving you the problem in a general sense, I'm considering that this capital F is any field. It can be the field of any field that you can consider over here, a general field. It can be the field of real numbers, it can be the field of complex number, it can be the field of rational numbers. If this is true, then it is true for any field. Okay, so I'm considering capital F to be field. By keeping this in mind, I want to check whether this particular structure is a vector space or not. So quickly, I'm going to go through the properties, and here the properties are as follows, as it is shown over here. Now I'm going to check the individual properties one by one after another. Now the first thing that you have to consider is that whether the matrix, this quantity, this particular part that you have written, that for each element x, y in V, there is an unique element x plus y in V. Now you see that when we take two matrices A and B from the set M cross n, okay, then these two matrices, this implies that it is automatically implying the fact that the matrix addition A plus B, this is the matrix addition I am defining. This is also a matrix, and it will be of order m by n, and it will belong to the set itself. I must write M cross n F and M cross n F over here. So it is quite obvious. It will happen always. If I consider any scalar quantity C from the field capital F, why it is happening? It happens because, as you know, that Aij M cross n, when added with another matrix Bij M cross n, then actually we get a matrix of this form Aij Bij M cross n, which is the matrix. We can consider this matrix as Cij M cross n, which belongs to M cross n F. And therefore, there is a to each pair of matrices there is a unique matrix of the form A plus B. Now, if I consider, this is point number one. Point number two is that if I consider C belonging to F and a matrix capital A belonging to M cross n F, if I consider this, then you see that we can, if I write Cij, if I write C dot Aij M cross n, you know each element of the matrix gets multiplied by the scalar, and therefore what we can do, we can write C dot Aij M cross n. This is also a matrix of order M cross n. Here I have actually used the notation dot, remember, because Aij is a scalar quantity, it has been taken from the field. C is the element which is taken from the field. So when C is outside the matrix, that means it is multiplying the matrix, it is going to multiply the matrix. That means that this particular notation has been used. This is the scalar multiplication. But when it is getting inside the matrix, it is getting multiplied by each and every element of the matrix. That means I have to use this notation. So I'm actually be very careful about what is happening, what type of operation that you are playing with. And if it is so, you know that this obviously belongs to M cross N F, and therefore two fundamental parts that have been written in the paragraph of the definition of the vector space that has been checked, and it is found that they satisfy the two properties. Now let us try to find out the properties which are defined one after another from VS1 to VS8. One important fact that you have to keep in mind, that the way I have written down the property, you have to follow this particular rule. So this is the sequence. You have to start with VS1 and you have to go up to VS4, and then only you can come to VS5. It is not like that you can try and arbitrary properties by choosing arbitrarily from anywhere. For example, if a particular student wants to find out whether this VS4 property is getting satisfied or not, two things may happen. One thing is that there is no meaning in testing whether VS4 is getting satisfied or not, because until and unless you justify the existence of 0 bar, that means you justify the fact that 0 bar is present inside the matrix, there is no meaning in checking VS4. Second point, it may so happen that suppose you are starting with by checking the property VS7, but somewhere before this VS7, suppose VS7 is getting satisfied, but before that somewhere, suppose in VS2 the property was actually not holding, but you have not checked it. You have directly when you have directly gone to check VS7, but your structure is not vector space, so this should not be. This may also happen. So you have to maintain the sequence, the order in which all the properties have been written. Okay, you cannot just shuffle the properties. Remember this in mind. So first of all, we are going to check the commutativity property. If I take two matrices A and B from M cross N F, you know that this matrix A will be denoted by Aij M cross N. This will be denoted by Bij M cross N. And if I multiply the two matrices A plus B by this if I add the two matrices by this operation, that means I'm going to add the two matrices in this manner, and this means that corresponding elements will get multiplied. But here I have used this operation, remember, and since this scalar quantities, these scalar quantities had been taken from a field, and a field is commutative with respect to the addition, so I can interchange the two terms. Right now you will understand why field is important. If you consider the set of integers z, it is not commutative with respect to negation operation. Because why? Because a minus b is not same as b minus a, so you'll not be able to prove this result. So if you want to write it as Bij plus Aij, that means your field needs to satisfy the commutative. You have to take the element, consider the elements from the field, because field is commutative with respect to commutativity of the scalar addition. So I am able to write this thing, and then we can again consider this to be Bij M cross N plus, again I am using this plus because it is the matrix are getting separated, and this is Aij M cross N, and we can write it as B plus A. So we see that matrix addition is actually commutative. The VS1 property is getting satisfied. Let us come to VS2. I am not writing it in details. Easily you can see in a similar manner, easily by choosing A to be Aij M cross N, B to be Bij M cross N, and C to be Cij M cross N. You can easily check by the way by which I have shown you that A plus B plus C is same as A plus B plus C. Easily can be checked. You just do it by yourself. Try to do it. Try to explicitly write it by yourself when you get the time. VS3. In VS3, we need to check about the additive identity. So we have to find out a kind of zero element. We need to find a kind of zero element in the set of matrices which will satisfy the property. So what zero element we can find over there? We can find a zero matrix, which is actually called the null matrix. And we know that zero matrix, the null matrix in short, can be denoted by 0ij m cross n. This zero is the number zero that has been chosen from the field of scalars. And this zero bar is the matrix itself. So we know that for this exists in m cross n f. And when we actually take any matrix, A, which is Aij m cross n, then A plus 0 bar actually gives you Aij m cross n plus 0ij m cross n, which is Aij plus 0. Remember what sort of plus I'm using, and that is Aij m cross n. So 0 bar is the null matrix, is the additive identity of the set m cross n f. This session is going to end very soon, so you again rejoin in the next session. Then I'm going to continue with this particular problem. I hope that so far you have understood what I have discussed. So in the next session, I'm going to continue. It takes lots of amount of time because it is not very easy task to do so. Okay, so let me stop over here.